Hello and welcome. In this video, we will apply transfer learning vision transformer model on CIFAR-10 dataset. In case you don't know what CIFAR-10 dataset is, we can search in Google what is CIFAR-10 dataset, and it will appear some search results. If we click on the first result, we will enter this website of CIFAR-10 dataset. So the CIFAR-10 dataset consists of 60,000 images. So we have 50,000 images for training and we have 10,000 images for testing. Okay, so the CIFAR-10 dataset consists of 60,000 images in total, each of size 32 pixels for height and 32 pixels for width, color images in 10 classes. So we have 10 classes with 6,000 images per class. There are 50,000 images training, so training images, and 10,000 test images. The dataset is divided into 5 training batches and 1 test batch, each with 10,000 images. The test batch contains exactly 1,000 randomly selected images from each class. The training batches contain the remaining images in random order, but some training batches may contain more images from one class than another. Between them, the training batches contain exactly 5,000 images from each class. So now we have read some definition about CIFAR-10 dataset. We can continue with this project. So the core idea of vision transformers, we can shorten it for VIT. So we can say VIT. If you hear someone say VIT, it's short for vision transformers. The core idea of vision transformers is that transformers were originally designed for NLP tasks. But vision transformer takes the same architecture and applies it to images by treating images or image batches like word tokens. So we will treat the image batches like word tokens. We need to convert our CIFAR-10 images into batches. So CIFAR-10 images are originally 32 by 32 pixels, but are resized to 224 by 224 by 3 color channels to match the input requirement of pre-trained vision transformers. Each image is divided into fixed size patches, typically 16 by 16 pixels. This results in 14 by 14, 196 batches per image. Each batch acts like a token, just as words do in language models. So each batch acts as a token. If you build a LLM model, you will divide a sequence of text into tokens. So we have here an image. We need to split or to segment this image into batches of fixed size batches, typically 16 by 16 pixels. The next step, we need to create batch embeddings. So each batch, which is of size 16 by 16 by 3 color channels, we need to create a 768 values vector. So we need to flatten into a 1D vector. We need to flatten this batch into a 1D vector. These vectors are passed through a learned linear projection layer to embed them into a fixed dimensional space. So dimensions equals 768. The output is a sequence of 196 batch embeddings ready to be processed like word embeddings in NLP. The third step is injecting positional information in order to retain the positional encoding, or to retain the positional content or data. We need to inject a positional information. Transformers alone don't understand the position of batches. Therefore, positional embeddings are added to each batch embedding. This preserves the spatial structure of the image. For example, top left versus bottom right. So to preserve the spatial structure or to keep the spatial information, we need to encode the position of each batch. Okay, so injecting positional information. Fourthly, inserting the CLS token. So CLS is short for classification. A special learnable vector called CLS token is added at the beginning of the sequence. This token acts as a summary representation of the entire image. Its final embedding after all transformer layers is used for classification. Okay, so we need to insert a CLS token, and this CLS token is a special learnable vector, and we need to add it at the beginning of the sequence. This token acts as a summary representation of the entire image. The fourth step, transformer encoder blocks. The full sequence, so 196 batch embeddings plus classification token, is passed through L transformer encoder layers predefined in the model VIT tiny batch 16 224. Each encoder layer contains multi-head self-attention, in short MSA, enables each batch to attend to all the others. Feed-forward networks, which is also known as multi-layer perceptron MLP, applies nonlinear transformations to the attended features. Lastly, we have residual connections and layer normalization which ensure stability and smooth gradient flow across the training. And then output and classification. This is the last step we have. After passing through all transformer layers, the final output vector of the CLS token is extracted. This vector is passed to a classification head, which is a linear or MLB layer that outputs 10 logits. So 1 logit per class, 1 per CIFAR-10 class. The class with the highest score is selected as the predicted label. So this layer will output 10 logits, and the highest logit, the highest score, is selected as the predicted label. We have here a nice visual way to represent how this vision transformer works. So step-by-step explanation of vision transformer architecture. As we said, we start with an image. We need to segment or to split this image into batches. And this process is equivalent to building NLP models. We need to convert texts into tokens. So the same idea applies here. We need to convert this image or to segment this image into patches. Secondly, we need to create embeddings, to create some embeddings of these batches. And then the third step, we need to add positional embeddings in order to preserve the spatial dimensions, to preserve the spatial contextual information. And then we need to add CLS token. As we said, CLS is just a token, a special learnable vector. The output of this CLS token will be a vector that we pass to transformer encoder layers. This transformer consists of 3 components. As we said, we have multi-head self-attention, we have feed-forward network, MLP, and we have residual connections and layer normalization. Then we pass the output of transformer to a classification head, which classifies it into 10 classes, 1 logit per class. Now, with that being said, we have gone through the conceptual overview of vision transformer. Now we will move into the practical into the practical section. So first of all, in order to build this project, we need a GPU. So we have to go to runtime. Now I am using Google Colab, okay? colab.research.google.com. And in order to use GPU, we have to go to runtime, then select change runtime type and choose L4 GPU, for example. Then we need to connect. Now it's connecting. The second step, we need to import the required libraries. So import the required libraries. This is a heading. The first library we need to import is Torch. So import Torch, then import Torch Vision. Torch Vision is the base domain library for PyTorch computer vision. Import, then import torch.nn as nn. Import, also we need import torch.optim as optim. Optim is a sub-library inside PyTorch that contains many popular optimizers in PyTorch. And then from Torch Vision, import datasets. Datasets contains many popular datasets inside Torch Vision, and we will load the CIFAR-10 datasets from or by using this datasets package, comma. Also we need transforms in order to apply some transformations on these images. And then we need to, from torch.utils.data, import data loader in order to convert our data into batches. So we have to import data loader. Also we need import TIM. TIM is a library that contains pre-trained vision transformer models. Import matplotlib. Also matplotlib is going to be fundamental for visualizations. Import matplotlib.pyplot as plt. Import numpy as np. We will need also from sklearn.metrics. Import confusion matrix, comma, confusion matrix display in order to display a confusion matrix that will help us visualize our model's performance. Import time. Now, with that being said, these are all of the tools that we will need in order to build this project. So let's import them. Let's go, click enter. Now we have imported all of these libraries, and we can check also some versions. So like torch.version __ version __, we will get this version. We have 2.6.0 plus CUDA version is 12.4, and also we can assure that we have Torch Vision by going torchvision.version 0.21.0 plus CUDA 12.4. So this is the version of Torch Vision library. And we can also make sure that we have the GPU ready to go by going NVIDIA-SMI, and nice, we have NVIDIA L4 GPU ready to go. So I think now we can move on to the next step. So what is the next step? The next step is we have to get a data. Now we need to get a dataset in order to build this model. So let's put a nice heading here. Step 1, getting a dataset. The dataset that we will be using is CIFAR, as we said, CIFAR-10 dataset. Now we have to create a variable called transform_train. This variable will be, we will use the library transforms that we have imported above, transforms.compose. So compose is a nice class that let us chain multiple image transformations in order to apply them on the images. Transforms.resize, for example, we need to resize the images because, as we said, CIFAR-10, the images that come from CIFAR-10 dataset are all 32 by 32 color images. So we need to resize them into 224 by 224 height and width. So we have to resize those images. The second step is we have to transforms.resize we have to convert our images into tensors in order to pass them to a model. So computers don't understand images as pure images. We need to convert them into numbers. We have to convert those images into some numerical form that the computer is able to understand. The third step, transforms dot normalize. We have to normalize our images. Now, why do we have to normalize our images? Well, normalizing our images is crucial because of three reasons. The first reason, help model converge faster. So when we normalize our images, it helps our model converge faster, and also matches. The second reason is that it matches pre-training conditions, because the vision transformer expects that the images are normalized, so it has a mean of 0.5 and it has a standard deviation of 0.5, so matches pre-training conditions. The third step avoids bias in learning, so it avoids bias in learning. And the last reason is that keeps numerical stability, so it keeps the numerical calculations or computations stability. So these are the reasons why we have to normalize our images. Okay, now we can run this. So we need to pass these operations inside the list. We have to wrap them. We have to wrap these operations inside the list. Okay, now let's run this. Okay, that's good. Now let's do the same for the test dataset. So transform underscore test equals transforms library dot compose. So composes several transforms together. If you read here the doc string, we can go Control Shift space if you are on Windows, or if you are on Mac, you can go Control Command space, and it will show this diagonal box, which gives us a brief overview of the class functionality. Composes several transforms together. This transform doesn't support Torch script. Okay, that's very nice. Now we have, as we said, we have to pass a list. This list will contain several image transformations, like for example transforms dot resize. We have to resize our images, as we said, from 32 pixels by 32 pixels to 224 by 224 pixels. And then the next operation is that we have to apply transforms dot to tensor. We have to convert our images into tensors in order to be able to pass them to a model. And then transforms dot normalize. We have to normalize our images into 0.5. This is the mean, as you can see here. This is the mean of the pixels, and we have to specify that the standard deviation as 0.5, and we can run. Now we have defined our image transformations operations. Now we can get our dataset. We can load our dataset. So let's create now a variable called train dataset. This variable will be datasets dot CIFAR-10. So we will use this class CIFAR-10. If we search here Torch Vision, so Torch Vision is the base domain library for PyTorch computer vision. Torch Vision, this library is part of the PyTorch project. PyTorch is an open source machine learning framework, and if you read here, Torch Vision is really good for computer vision because it contains multiple different datasets for computer vision tasks. If we click on this datasets tab, we can read in here, Torch Vision provides many built-in datasets in the Torch Vision.datasets module, as well as utility classes for building our own datasets. So that's very nice. We have this datasets library, and it contains many built-in datasets in the Torch Vision.datasets module. Like, for example, we have image classification datasets, for example, Caltech 101, and we have CIFAR-10, which we are using now. We are using CIFAR-10 dataset. There's also CIFAR-100, contains 100 different classes, and there are a lot of different datasets from or inside Torch Vision datasets. Okay. Also, we have some datasets that are used for image detection or segmentation, and so on, so on. So now we will use. So Colab is giving me this notification because it's saying, "Hey, warning! You are connected to a GPU runtime, but not utilizing it." So we have to, if you are connecting to a GPU, we have to utilize it as fast as possible. Okay, we can go now. CIFAR-10 and then root equals train or data. So the root is where to download the data. Where do you want to download the dataset? Okay, so the name of the directory that will be here. You can name it anything you want. For example, my data, or you can go, for example, CIFAR data. But I'm going to name it as data. So this is the root, and then we have to pass in here whether we want the training version or the testing version of it. So train equals true. Now we want to load the training dataset. So we need to specify train as true, and then we can go download equals true. Do you want to download it? Yes, I want. So here, do you want to download the data? Yes or no? In this case, yes, we do. And then transform. What transformations do you want to apply on these images, on the training images? Well, we have created a variable here called transform train. We need to apply this series of transformations on the training images. So we need to pass the name of that variable. So transform underscore train. And then target underscore transform, we can set it as none, equals none, or it's by default it's none. Okay, so you may want to specify it, you may not. It's by default none, so we may cancel it. And now we can run this safely. It will load our train dataset. Okay, so it's now loading the train dataset successfully. You can notice here it's 170 megabytes by 170 megabytes. We need to do the same thing for the test dataset. So test underscore dataset equals datasets dot CIFAR-10 classes, or class CIFAR-10 class. This is a class that we need to pass in here root equals data, and then train. Do you want to load the training version or the testing version? In this case, false. I want the testing version of the CIFAR-10 dataset. Download. Do you want to download it? Yes, we do. And then transform equals test underscore transform. Test underscore transform. I think we have misspelled this variable here. Oh, it's transform test. So transform underscore test. Now we can run this, and it's loading our test version. Now we have loaded our data successfully. We can go train dataset, and it will return this kind of information. So we have dataset CIFAR-10, number of data points 50,000 images. So you have in the training version number of data points as 50,000 images, and the root location is data split train. So this is the split for training, and the transformations that we have applied to the images are these following transformations. Firstly, resize the images, and then to tensor. We have to convert those images into tensors, and lastly, normalize. So mean 0.5, standard deviation 0.5. So this is the train dataset variable. If you show the test dataset, it will be the same, except that the number of data points is now 10,000. So rather than we have a number of data points here 50,000, we now have number of data points 10,000, and the same setup of compose for transformations. If we check this file section, you'll notice that we will have this data folder. This data folder contains some files about this dataset of CIFAR, you can notice that we have 5 batches: batch 1, batch 2, batch 3, batch 4, and batch 5, the same as we have read in here. So we have read that we have here 5 batches. Yep. The training batches contain the remaining images in random order, but some training batches may contain more images. Okay? Yeah, here. The dataset is divided into 5 training batches and 1 test batch. So we have 5 training batches and just 1 test batch. Here we have 1, 2, 3, 4, 5. These are all training batches. And 1 test batch. And 1 test batch. Okay? The next step, we need to convert our data into data loaders, into batches. So why would we do this? Now we have the second step: convert datasets into iterables, batches. If we write in here, right now, our data set or our data is in the form of PyTorch datasets. Okay? We need to convert these datasets into data loaders. In other words, iterables. But what is a data loader? If you recall that a data loader turns our datasets into Python iterables. Okay? Now the question, why would we do this? Why would we do this? Well, for 2 main reasons. The first reason is that it is more computationally efficient, as in your computing hardware may not be able to look, in other words, store in memory at 60 or 50,000 images in one hit. So we break it down to 64 images at a time. So a batch size of 64. Now, if you have a powerful GPU, it will be able to look at all 64 images at a time, or all 50,000 images at a time. But in many cases, your RAM or your memory wouldn't fit this amount of images. So your memory will not be able to store all 50,000 images in that memory at a time. So it would be helpful to convert our data into batches, into subgroups, into mini batches, in order to be more efficiently. So it is more computationally efficient, as in your computing hardware. So your RAM, your memory, your computing hardware may not be able to look, in other words, store in memory at 50,000 images in one hit. So we break it down. We need to break our dataset down into batches, into groups, into mini batches. And each batch is of size, in this case, I'm going to make it 64. So each batch contains 64 images at a time. So the model will be able to handle or process those images more efficiently and more effectively. The second reason, it gives our neural network more chances to update its gradients per epoch. So rather than the model sees all 50,000 images in one epoch, and then after the model has seen all those images, it will update its weights. No, we want it after each batch, after each after the model sees 64 images, then updates its weights, its internal states, rather than one update per epoch, we will have many updates per one epoch, and that will be helpful in order to refine our weights and our biases more and more. So it gives our neural network more chances to update its gradients per epoch. So these are the main reasons why we would need to convert our datasets into batches. So convert datasets into batches, into iterables. Now let's do that. We need to from torch. So we have imported above, so we can import it again from torch.utils.data import data loader. And then, so this is for demonstration purposes. We have imported it above, but for illustration, I'm going to import it again. So we need from torch.utils.data, we need to import our data loader class, and then set up the batch size hyperparameter. So batch size equals 64. Now you may have a question, why you have write this variable name all in capitals? Well, it's a convention in the world of machine learning and in the world of data science that you will see a lot of people write the names of variables of hyperparameters as capitals. So this is like a convention or like a standard practice in all of machine learning ML DL projects. So now let's convert our datasets into iterables. In other words, batches. So batchify our data. Now we will create a train loader equals data loader class, and then pass in here. So data loader is a class that takes from me three important parameters. The first parameter is dataset. So which dataset you want to apply this data loader on. In this case, we will apply it on the train dataset, comma, which is CIFAR. If you hover over this variable, it's a CIFAR-10 dataset. And then batch size, we need to specify a batch size equals this batch size variable here, batch size variable 64, comma, and then do you want to shuffle the data? So in this case, yes, true. We want to shuffle the training data, comma, how many num workers do you want to use? I'm going to use 10. So I want to specify num of workers equals 2. So this is for training. Let's do the same thing for testing. So test underscore loader equals the class data loader. We will use the class data loader in order to convert our datasets into data loaders. And then, as we said, it receives from me three parameters. The first parameter is dataset equals test dataset. In this case, the first data loader, we have applied it on train dataset, but in this time, we need to apply this data loader class on the test dataset class, on the test dataset variable, comma, batch size, so the number of batches. So batch size is the same as how many samples in each batch. So how many training examples or testing examples in each batch. In this case, it's the same as our hyperparameter here. So batch size 64, and then shuffle. Do you want to shuffle the testing data? No, we don't. We don't want to shuffle our testing data. Shuffle equals false. Why we wouldn't shuffle our testing data, or why we don't need to shuffle our testing data? Well, because our model will not see our test data during training. Our model will not see our testing data or test images during training. So we do need to shuffle our training images because we don't our model to learn the order inside the data. So say for example, maybe we will have all of the airplane images, okay, all of the airplane images in order, then we will have all of the automobile images in order, then we have all of the bird images, and then cat images. In that case, our model will learn the order of the images. But now, in this case, we don't our model to learn the order of the images. we wanted to learn the individual patterns between each class and then be able to classify or distinguish between different classes. Okay, but in the case of test data loader, we don't need to shuffle it, so we don't need to make the operation take more time to shuffle the data. Okay, because we don't need that. We need just to shuffle our training data loader in order for the model to not learn any order in the data. And then we have to specify num workers as 2. Now we can run that and we can check out what we've created. Let's check out what we've created. Print train or data loaders. Let's print our data loaders. Train loader, comma, test loader. So these are our test and train loaders. If we run this, we will have a tuple containing 2 data loaders. So we have here torch.utils.data.dataloader class object stored at this location in the memory, and we have this also the same thing, torch.utils.data.dataloader object stored at this location in the memory. So we have 2 data loaders ready to go, which is very nice. And then print, if you print also a length of train data loader, and then length, we print the length of train loader. So this is the length of batches of this size, which is batch size, ... And then we have print length of test data loader, which is the length of test loader batches of batch size. So this kind of output is really fun because it shows you how many batches do you have in your dataset. If you run this, ooh, that's interesting. Length of train data loader, we have 782 batches. Each batch is of size 64 images, and we have the length of test data loader, we have 157 batches of 64 samples in each batch. So if we change this, the batch size, say for example, each batch will only contain 1 sample. How many batches will we have? If you run this now, how many batches will we have if we have changed this batch size hyperparameter variable into just 1? Well, depending on the length of the CIFAR-10 dataset, we will have 50,000 batches of size 1, and we will have 10,000 batches of size 1 for the testing data. Now let's run. Yes, now we have 50,000 batches of each batch just contains 1 sample, and we have 10,000 batches. Each batch contains 1 sample in the case of the testing data set. So choosing the hyperparameter, choosing this value is depending on the machine learning engineer. We as machine learning engineers, as deep learning engineers, as data scientists, we need to tweak or to fine tune these hyperparameters like the batch size and choose the best performing batch size. So this is a hyperparameter that you as a machine learning engineer need to tweak, need to fine tune, need to choose the best value depends on your experiments. So we need to experiment in order to reach to the optimal values for these hyperparameters. In this case, I'm going to try 64, and we will have now 782 batches of 64 and 157 batches of 64 images. Now let's move on to the next section, or the next step. The next step, now we haven't visualized any images. We haven't visualized any of our datasets or our images. We need to visualize. Always visualize. So step 3, visualize some data. Now, if we have visualized the train data, it's just, or train dataset, it's just a dataset object inside PyTorch, and if you want to access the first index, it will return the first image. So we have one tensor. This tensor is representing an image, and we have a label that this image belongs to. So this image now belongs to this class. If you want to know what classes do we have, so we haven't checked what classes do we have. If you go train dataset dot classes, it will return a list that contains all of the classes that we have for CIFAR-10. We have airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. So we have 10 classes, and if you want to know what 6 means, so what 6 means, we might want to use a property in the train dataset that is called class to IDX. So we have this property or attribute, class to IDX. This property will retain a dictionary, each class or each category and its associated number. So 6 means frog. Ooh, so this image relates to a frog. If we need to visualize this image, we need to know the shapes. So what is the shape of our image? If you go train dataset at index 0, we will get a tuple. We can unpack this tuple into an image, comma, label. So we need to unpack this tuple. Now we have an image, which is a tensor, a PyTorch tensor. This is a PyTorch tensor. And if you want to get the shape of it, we will go image dot shape, and we can get this shape. So this image or its shape is 3, 224, 224. PyTorch uses this kind of order for shapes of images. It starts with channels, with color channels, and then height, and then width. So alphabetical order. So we have height, and then we have width. Okay. But Matplotlib, unfortunately, Matplotlib expects this shape to be in the order of height, width, channels. So if we tried to visualize this image using Matplotlib by going plt.imshow and then pass in here image, we will get an error. And this error is saying invalid shape 3,224,224 for image data. So that's a really bad thing. We need to reorder these shapes or these dimensions in order to be able to visualize it. So why don't we create a function? Why don't we create a function by going def and then name it, for example, plot image? And this function will take from me a parameter image. And then we need to, first of all, now because we have normalized our images, okay, if you visualize this image again, we have normalized our images, so we have negative values. Okay, we have negative values. We need to unnormalize these values. And if you forget about this, remember, we have normalized our images using this transformation. We have done some data normalization on the images. So by going transforms.normalize, and we have make the mean 0.5, and we have set the standard deviation as 0.5. So we need to unnormalize this image tensor in order to be able to visualize it using Matplotlib by going image equals image and divide it by 2. So we need to divide the image by 2 and then add 0.5. So this step is unnormalizing the image. The next step is we need to convert, as we said, this image is now in the form of PyTorch tensor. If you pass this image to a type function, we have a torch tensor. And Matplotlib doesn't work with PyTorch tensors. It needs to work with NumPy arrays. So we have to convert this image from a PyTorch tensor into a NumPy array by going np_image equals image.numpy. And that's really easy. You have just you just need to call .numpy on the tensor, and it will convert this tensor into a NumPy array. Notice we have now an array rather than tensor. The next step, now we are able to visualize it using mshow. So by going plt.mshow, mshow is a function or a really helpful function inside matplotlib that allows us to visualize images, enables us to visualize images. So we need to pass in numpy.transpose. As we said, PyTorch deals with images in the form of channels. If you write here, PyTorch deals with images in the form of, and put it in a tilde or backticks, and then put here channels or color channels, comma height, comma width. Okay, so this is the form that PyTorch prefers. PyTorch prefers this kind of order. It prefers the first thing, color channels. So how many color channels do we have? Comma height, the height of the image, and then the width of the image. But matplotlib works with images in the form of, and then put some backticks, and then by going height, comma width, comma color channels. So in order to rearrange this these dimensions, in order to rearrange this kind of order, we have to transpose the array and then pass here the numpy image, np underscore image, np image, comma, and then define the shape of it as 1, 2, 0. So this is the kind of rearrangement that we want. We want to put the height, which is now currently in the position 1. We need to put it in the first position, and then width, which is 0, 1, 2. We need to put the width here, and then channels, we need to put it in the last dimension. Okay, and then lastly, plt.show. Now, I think this function will work for matplotlib. If you try now to use this plot image function and pass our image, it's now able to visualize this image. Oh, numpy has no attribute transpose. I have misspelled transpose. Okay, now let's run again, and yes, we have this image of frog. So now we have created an image that, or created a function that is able to deal with tenses which represents images in the form of torch tenses, and convert them into numpy arrays and use them in the plot image function in order to plot these images correctly and successfully. So we may also want to use a plt axis, plt.axis, and pass false in order to hide these axes. So x-axis and y-axis, like this. Okay. Now the next step, why don't we go ahead and get a batch of images? Okay, so get a batch of images by going train features batch, comma train labels batch equals, so equals the train loader, or the next, we have to pass it to next, and then eta, and then pass our train loader. So we need to pass our train loader into the function eta. We need to convert our train loader data loader into an iterable, and then get the next batch. We need to fetch one batch from this image, from this data loader. Now if you visualize our train features batch, comma train labels batch dot shape, we need the shape. It will be, yes, we have 64 images. Now this is a whole batch. We have 64 images. Each image has 3 channels, 3 color channels, red, green, blue, and its height is 224 by width 224. And we have also 64 labels. So we have 64 images associated with 64 labels. Okay, so this is the shape of one batch. We have train features. So features, I used features to refer to images, samples, and I used labels to refer to the labels or targets. Now if we visualize train labels batch, it's just a tensor that has 64 labels and 64 different labels representing or each associated with a different image, with an image inside this batch. And we can also create a mechanism to each time select a random sample from this batch and visualize it. We can go visualize one sample from a batch. We need to first of all create a variable and name it random idx. Random idx equals torch.randint. So we will generate a random integer starting from 0 to the length of this batch. So what is the length of this batch? If we visualize the length of train features batch, how many images do we have in this batch? We have 64 images. So we need to generate a random integer starting from 0 until the length of this train features batch, and specify the size as 1. We need to fetch just one image and get the item. Now if you visualize this random idx, it's just a random integer. Each time we generate a random number between the length between 0, in the range of 0 to the length of train features batch, 39, 44, and so on, so on. Now the next step is we need to get an image, comma, label. We need to unpack the train features batch and pass in here index on the random idx, comma, train labels batch, and index on the random idx. We will get an image and a label. And then we can go ahead and use our function plot image and pass our image. And then we can go also, we can pass a label in here, label, and we can change our function to accept a label, comma, label, and then plt.title class names. Or we can store our classes, which is train dataset. This is a dataset. We can get our classes by using the attribute classes dot classes. We can get a list of all of our classes and store them in a variable called class names. Now we can use this variable in order to class on it by using the label. Now we can pass the label in here. So pass label. It's a frog now, as you can see, and we can use now this label and pass the label of the image to this function, and it will show us the label. Now we have a frog, and now if we rerun it, we have a deer. Rerun, we have a sheep, and so on, so on. So each time we have a cat. Each time we run the cell, we will get a different image with a different label. Now we have a horse, and so on, so on. Now we have visualized our images. Now we have visualized just one single image, just a singular image. What about if you want to visualize multiple images at a time? We can do that easily now by going fig equals plt.figure. We need to create a figure. Fig size equals 9 by 9. We will specify our figure size as 9 by 9, and then go rows, comma, columns. We will specify the number of rows and the number of columns as 4, 4, and then go for I in range, start from 1, because the subplots doesn't start from 0. We have to start it from 1 and stop. We have to multiply rows times columns plus 1. So this is a fun way to visualize images. First of all, we need to index on the train dataset. So we will go random idx equals torch.randint, start from 0 to the length of train dataset, and we need to specify the size equals to 1. So we need to generate every time just one integer and get the item from it, and then index on the train dataset. So we have an image, comma, label, and index on the train underscore dataset, and get the random idx index, get the get the item at this index, and we will unpack that tuple into an image, comma label, and use our function plot image and pass the image, comma label. Now we will get, oops, we haven't specified the subplots. Each time we need to specify fig.add subplot as rows, comma columns, comma I. Now we will get fig.add subplot rows, columns, I. Yeah, because now this function will create each time a new figure. We will remove plt.xshow for now in order to be able to visualize it as one figure. Yep, now we have one figure. So if you want to visualize multiple images in one figure, we can go like that. Now we have a horse, cat, horse, deer, horse, and so on. Each time we run the cell, we will get different set of images. We have 4 rows by 4 columns, as you can see here. We have 1, 2, 3, 4. 4 rows by 4 columns, 1, 2, 3, 4. And each time we run the cell, you can also, we have automobile, we have a red car, blue car, we have a truck, frog, and so on. We have a truck here, and each time we run this, we have different set of images. So we have truck, deer, cat, and so on. So it's nice to visualize these images, and it's so fun to visualize multiple images at the first of any machine learning project. So at the start of any machine learning project, you need to build a mental model before building a real model using machine learning. Why? Because you may notice that there are some images with damaged pixels, or there are some images that are not belonging to that class. So maybe this image is not belonging to a cat. So you might find some issues with the labeling or some issues with the images that you could fix, because because the quality of data will define the quality of the model. So we have a rule in machine learning: garbage in, garbage out. If you feed the model garbage images, it will predict just garbage. But you need to make sure that the quality of data is really good in order for the model to predict really good predictions, or to produce really good outputs. Okay. Now I think that we had enough visualizing these images. We can move on to the next step, which is creating our model. So now let's create our model. We will use transfer learning. Okay. Now the step number, I think we have reached the step number 3 or 4. Yeah, we have here step 3, visualize some data. We have visualized some data. Now we can go step number 4, get the model. So we will use transfer learning in this lecture or in this video by going model equals TIM, which is TIM library contains multiple pre-trained vision transformer models dot create model function, and then we have to pass in the model name. So which model you want to fetch or you want to get. We need to get the VIT vision transformer underscore tiny underscore patch 16 underscore 224, and we need to set the parameter pre-trained as true. Yes, we want the pre-trained version of the model. And then we need to set, or we have to set the num of classes. So how many classes do we have? How many classes do we have in CIFAR-10? If we get the length of class names, we have 10 different classes in CIFAR-10. So we have to use this amount of classes to set our parameter num classes. So num classes equals length of class names, class underscore names. Now if you run this, it's now loading our model from Hugging Face. As you can see, it's loading our model from Hugging Face platform, and model 100%. So it has loaded our model. You can see here it's 22.9 megabytes out of 22.9 megabytes, which is really nice. So now if we visualize our model, ooh, that's the architecture of our model. So it's really a big architecture. You can see here we have batch embedding. As we said before, we have an embedding layer. We have the kernel size, which is of size 16 by 16. So we have here a convolutional layer, a conv 2D layer. We have 3 input channels. So we input to the model an image of 3 channels, red, green, blue, and it produces 192 outputs, or this is the number of out channels. So this is in channels, these are out channels, and then we have kernel size 16 by 16, and we have stride of 16 by 16. So each time we step over 16 pixels because we have the batch size as 16 by 16. And we have here position drop, we have some dropout layer, identity, then we have a sequential model, which is of block. We have layer normalization, we have a tension layer, we have a linear layer, and all that. All these layers are within the vision transformer, tiny VGG or tiny VIT vision transformer model, which is we are getting from the Hugging Face or TIM library. Okay, now we can also visualize the weights of the model. So we can go model.stateDict. So these are all of the weights within the model. If we scroll up, we have all of these weights and biases. So a massive amount of weights, very large amount of weights. Now we can see here we have CLS token, so classification token. These are all of the weights inside the classification token, because classification is a special learnable vector that we use in our VIT vision transformer architecture. You can see here we have a lot of weights and biases. Now that we have loaded our model successfully, we can move on to the next step, which is setting up device agnostic code. So this is a really important step in PyTorch. Now we have reached 5, setting up device agnostic code. So we can go now, device variable, device equals torch.device, and use CUDA if torch.CUDA.isAvailable function .is available, else use CPU. Now if we visualize device, what device do we have? Yes, we have device of type CUDA. So that's very nice, because if you visualize here NVIDIA SMI, what GPU am I using right now? I am using NVIDIA dash, yep, I have a misspelling, NVIDIA dash SMI. We have NVIDIA L4 GPU. Okay, so right now I am using NVIDIA L4 GPU, and when we said that torch.device CUDA, yes, it's available. If torch.CUDA is available, then make the device of the torch as CUDA, else CPU. It said yes, you have a GPU ready to go, which is of type CUDA. Okay, you have a device of type CUDA, and the GPU type is NVIDIA L4. Okay. Now we need to move the model, or to send the model into the device, because right now if we check model.device, I think this model is not yet on the GPU, because this model is now being on the CPU. We have to send it .to and send it to the device as like that. Okay, so model.to device, and then assign the model to the variable model, like that. Now if we check the model, now this model is being on the GPU device. The next step now is we need to set up our loss function and our optimizer. So creating step 6, creating a loss function, and optimizer. So quick question here, what is the role or the purpose of a loss function? Why do we have to use a loss function? Well, a loss function measures how wrong our model's predictions are, or measures how wrong our model is. So we can go NN, so the library of neural networks dot cross entropy loss. So a loss function measures how wrong our model is. That's as simple as, or as a basic definition as possible you can get for a loss function. So a loss function simply measures how wrong our model is. And an optimizer, what is the purpose of an optimizer? Well, the purpose of an optimizer is that our optimizer will update the gradients, will update the weights and biases for the model in order for it to better represent the data. Okay, so we need to go torch.optim.adam. We will use Adam optimizer and set the params equals model.parameters, okay, comma, learning rate. So learning rate is another important hyperparameter. So learning rate is an important hyperparameter that we as machine learning engineers or as deep learning engineers, we have to find the best value that achieves the maximum possible accuracy and the lowest possible loss. So learning rate is another important hyperparameter. So you have batch size, we have learning rate, the number of epochs. These are all important hyperparameters we need to tweak and try different values. So learning rate equals 0. Or we can go with this kind of writing as 3e-4. So we have to set the learning rate as 3e-4. Now we can run this and we get here a successful execution. Now if you check what loss function do we have cross entropy loss. So because or since we are dealing with multi-classification problem, we have 10 classes, we have to use cross entropy loss. Okay, so cross entropy is useful for training multi-classification problems. If you search here cross entropy loss, we have PyTorch. This is a cross entropy loss. So this criterion computes the cross entropy loss between input logits and targets. Note here, it's useful when training a classification problem with C classes, so with number of classes, with n number of classes. While if we were dealing with binary classification problem, we would use binary cross entropy. So this is a binary cross entropy PyTorch. We have a BCE loss. So if we are using or if we are dealing with binary classification data, we would use BCE loss. But in this case, which is binary, which is short for binary cross entropy loss. But in this case, we are dealing with multi-classification dataset. We have 10 classes. If you visualize our classes, here we have train dataset classes. We have this number of classes: airplane, automobile, bird, cat, and so on. Or if you visualize class names, we would get the same list of classes. But in this case, we are using multi-class classification, so we have to use cross entropy loss. And Adam optimizer is really good for classification, for computer vision classification problems, and we need to pass it learning rate of 3e-4, which is, if you type here 3e-4, it's just 0.003. So we want to use 0.0003 learning rate as the learning rate. Okay? Now the next step is I think we have got all of the pieces of the puzzle to be able to train our model. So now let's go the step number 9, I think, or step 6. Now step number 7. Step number 7, training our model. So let's create a function def train underscore model, and then pass in here model, comma, loader. We need a model to train it. We need a loader to train the model on this loader. We need a criterion to compute the loss of the training. We need so criterion is another word for loss. PyTorch terminology uses criterion as an interchangeable word with loss. And then we need an optimizer to optimize our training. We need to set the number of epochs as 5. So let's try 5. Let's go with 5. And then we need to set the mode of the model as training. So set the module in training mode. We have to set the mode of the model in training mode. Okay, set the module in training mode by using model.train function. So set the mode of the model to training. The next step is we have to create a for loop. So let's build our training loop for epoch in range of epochs. And then we have to set the variable running loss. So this variable will accumulate the loss. We have running underscore loss equals 0. We will initialize this variable to 0, to the value 0. And then for inputs, for each inputs, comma, labels. So inputs variable will be a batch of images. So this inputs variable will contain a tensor of 64 images. And this labels variable will contain a tensor of 64 labels. So for each batch of inputs, comma, labels in the loader, we will first of all move inputs, comma, labels to the device. We will move the inputs and the labels to the target device. Okay, so we have to move, first of all, we have to move the inputs and labels to the target device, which is really important in PyTorch. If the model is living on the GPU, the data must live on the GPU for the model to be able to compute it. Because if the data was on the CPU and the model was on the GPU, or vice versa, we will have a device mismatch error in PyTorch. And we know that we have the 3 chief problems in machine learning. We have device mismatch errors, we have shape mismatch errors, and we have data type mismatch errors. These are 3 of the most common errors you will face in the world of machine learning. So inputs, comma, labels equals inputs dot to. We have to send the inputs to the target device, comma, we have to send or move the labels or transfer the labels to the target device. And then optimizer dot zero grad. We have to zero the gradients of the optimizer. For each batch, we have to reset. If you read here the documentation, we have to reset the gradients of all optimized torch.tenses. Okay, so we have to reset the gradients of all optimized torch tenses. In each loop, we have to reset the gradients or zero the gradients. The next step is we have to do a forward pass. So let's go forward pass. Outputs equals, so the outputs of the model equals model. We will use our model that we pass into this function. We will use it and pass the inputs, the images, the photos, the pictures. We will pass the images, the pictures, the photographs into the model, and then the model will make some predictions and store it in this outputs variable. And then the next step, so I think here we have 1, 2, forward pass. The third step, we have to calculate the loss. We need to calculate the loss per batch. Note this loss per batch. So we can go loss equals loss function. We will use our loss function, which is cross entropy. Remember, this criterion computes the cross entropy loss between input logits of the model and target and the real data. So you have to pass in here, we have to pass in outputs of the model and compare them to the labels, to the ground truth labels of the data. Okay, and then this loss function will calculate the loss, okay, between the loss or the cost between the outputs of the model and the labels or the ground truth real labels of the dataset. The fourth step, we have to do a loss backward, so perform back propagation. So loss dot backward in order to compute the gradients with respect to all of the parameters in the model, okay, using the chain rule. If we search here, or if we can get the doc string here backward. So this back propagation algorithm will perform a back propagation to the model's weights and calculates the gradients of the with respect to all of the weights and biases in order for the next step, which is perform gradient descent. This algorithm will use our optimizer.sep in order to update the weights and biases to better represent the data in order to be able to fit the data. Okay, so we will perform a gradient descent algorithm. Lastly, we have to accumulate running loss. We have to accumulate the running loss plus equals loss. So loss.item accumulate the loss. So we have to, for each batch, we need to calculate the loss between the model's outputs and the real labels, and then add that to this variable, running loss, in order to have the total loss for all of the batches, in order to calculate the total loss across all batches. Because this loss is going to be specific. This loss is going to be specific to each batch. So this loss is going to be computed on each batch, but we need to accumulate the total loss using this notation, which is plus equals. Very important. You have to put plus equals, not just equals, because if you put equals, that will this will reset the running loss each time to the loss specific to that batch. So we have to accumulate it. We have to calculate the loss accumulatively in an accumulative way. The last step is we have to print out epoch, the number of the epoch we have reached. So epoch, and then print the loss, running loss. We will divide the running loss by the length of data loader. Why we are dividing the running loss by the total length of the data loader? Well, because we are accumulatively adding those losses to the running loss, and then we will have here, this variable will contain the total loss across all batches. So we will have a very high number. Then we need to scale it. We need to normalize it. We need to get the overall loss across all batches by dividing it by the length of loader in order to have the mean loss or the average loss across all batches. And then we have to get the first four decimal places by using this notation, colon 0.4f, and note that this epoch starts from 0. We have to add 1 to it in order to go epoch 1, epoch 2, start from epoch 1 rather than starting from epoch 0. With that being said, I think now we have created a fully working function to train our model. So let's run that, and now let's call our function train model and pass our model, pass train data loader, because we have train loader. Yeah, we have called it train loader, we need to pass in criterion, which is our loss function, we need to pass our optimizer that we have created above here. We have created a loss function, we have created an optimizer. So we need to pass this loss function and this optimizer to the train model function. Now we can train our model. 3, 2, 1, train. and now it's going smoothly. As you can see in here, we have some functions running. Train model. So I think this train model will take a fair bit of time. So I will stop here until the model trains, and I will be back after the model finished training. So now we're back. As you can see in here, we have epoch 1. The loss was 0.30. And then we have epoch 2. The loss was 0.18. The loss has decreased, as you can see in here. Epoch 3, we have loss 0.14 or 0.15. We have epoch 4, loss 0.12. And lastly, epoch 5, the loss is 0.10. So we can notice that we have a great decrease in the loss, going from 0.30 to 0.10, which is very nice. So the loss is decreasing. Now we need to build a function to evaluate the model. So let's go def evaluate model, evaluate underscore model. This function will take from me 2 parameters. The first model and the second is loader, loader. Now the first step is we need to turn the mode of the model into evaluation mode by going model.eval. So we have to turn on the evaluation mode of the model. Okay, set the module in evaluation mode by using .eval function. Eval is short for evaluation. So set the mode of the mode of the model into evaluation mode. The next step is we need to create a variable correct equals 0. We have to initialize a variable called correct. So the number of correct predictions equals 0, and then the total number of predictions equals 0, and then we have all underscore predictions. We need to initialize this variable to an empty list. Okay, all pred, and then all underscore labels equals an empty list. Then we have to use with torch.inference mode. We need to use inference mode. So inference mode is a context manager that enables or disables inference mode in PyTorch library. So we have to turn on inference mode. And then we need to create a for loop for inputs, labels in loader. The first step is we have to move the inputs and the labels into the target device. We have to put the inputs and the labels to the target device in order to be able to interact with the model. So inputs, labels equals inputs dot to. So send inputs to the target device, labels dot to device. The next step is we have to do a forward pass. We have to pass the images, the photos, the pictures to the model, and then make some predictions. So outputs equals model. We have to use this model and pass the inputs, which are the images. So do a forward pass through the model. And then we have to create a variable and name it as underscore because we don't want to use it, predicted equals torch.max. We need to use the max function in PyTorch and pass it outputs.data. And then we need to specify here 1. Total plus equals, we have to accumulate on the total variable, plus equals labels.size at index 0, or we have to pass 0 to the size method. Here you can notice labels.size function or method, and then pass 0 to the labels size or to the method size, and then correct plus equals, we have to accumulate on the correct by going predicted, if predicted equals labels dot sum. We need to sum, and then dot item, we need to get just the value inside that tensor by using the item method. and then we need to use all preds list and extend this list using the extend method, and then pass in here predicted dot CPU. We have to move our predicted variable to the CPU device by going dot CPU method, and then we have to turn it into numpy by going dot numpy. So numpy method returns the tensor as a numpy nd array, which is short for n-dimensional array in numpy. And then all underscore labels dot extend, the same thing. We need to extend this list, all labels, as we have extended our all preds list by going dot extend method, and pass in here labels dot CPU dot numpy method. Now we need to get out of the for loop, but still within the with torch inference mode context manager. Okay, so we have to go outside of the for loop, but still we are still within the torch inference mode context manager, and create a variable called accuracy equals 100 times correct divided by total. So the accuracy method is the correct, the number of correct predictions divided by the number of total predictions, and then times 100 in order to get a percentage, the accuracy as a percent. And then print f string accuracy, so the accuracy of the model, which is accuracy, and then get just 2 decimal places, and then put a percent sign. Return, we need to return all labels, all underscore labels, comma, all underscore predictions. Now we have created our function. Now let's run the cell, and then let's call our function. We need to create a variable labels, comma, or comma, predictions equals the function evaluate model, and then pass in here model, comma, test loader. So we need to pass our test loader, our test underscore loader, data loader. This is a data loader we have created earlier, which is a torch.utils.data.data loader, and pass it to the model. So we need to use our model, our trained model, in order to predict on the test loader and make those predictions and evaluate our model using this function. Now let's run our function. It will print the accuracy as we have said in here, or as we have specified in here. It will print the accuracy of the model. As you can see in here, hooray, we have accuracy of 91.99%, which is really good accuracy. Okay, if we want to visualize our labels, these are the labels that we have. So we have label 4, 3. So these are the classes. So we have class number 1, class number 3. These are the labels, the truth labels of the dataset. And if we check out preds, the predictions, these are the predictions of the model. So we need now to create a confusion matrix to visualize the difference between our truth labels, our ground truth labels, and our predicted preds. We have got these variables from this function because we have returned all labels, comma, all preds, and then we have unpacked. So this will return a tuple. When we put a variable, comma, variable, it will return a tuple, and then we will return that tuple, and we will unpack it here. We have done unpacking labels, comma, preds, and we have got these labels and preds as predictions from the model. Now let's move on to the next step and visualize a pretty confusion matrix by going CM, which is short for confusion matrix, equals confusion underscore matrix function. We have gotten this function from scikit-learn. So we have imported from sklearn.metrics import confusion underscore matrix. So we have this function inside scikit-learn. If you search in here, confusion matrix sklearn, we have this documentation, confusion matrix inside scikit-learn, as you can see in here, sklearn.metrics.confusion underscore matrix. So compute this function. What it does, it computes confusion matrix to evaluate the accuracy of a classification model. By definition, a confusion matrix C is such that C I, j is equal to the number of observations known to be in group I and predicted to be in group J. So it takes from me, this function receives from me Y true, the ground truth labels, the truth labels or targets, and takes from me predictions, the model's predictions, the model's outputs, and then computes or calculates a confusion matrix. So that's very nice. Now let's go ahead and pass in here y underscore true equals labels, the truth labels, the real labels, and compare it. We need to compare it to the y underscore pred, so the predictions of the model, the outputs of the model. Y underscore pred equals preds. And now if we run the cell and visualize this CM, we will get a confusion matrix. As you can see here, it's a NumPy array that contains a confusion matrix. And if you notice here, we have the highest values or the greatest values in the diagonal, which is really nice to have really high values in the diagonal. That means this diagonal represents the truth values, or represents the truth predictions, or represents the predictions that the model has got it correct, or has got it in a correct manner. So we have these values, 942, we have 970, 980, 11, we have 822, and so on, so on. So the highest values are lying on the diagonal in here, on here. Now let's create a pretty visualization. This is, yes, this is a confusion matrix, but it's not pretty. How to make this confusion matrix prettier? So let's put a comment here. Let's make this confusion matrix prettier. And then let's use an emoji of something pretty, like a butterfly. And then let's go ahead. Disp equals confusion matrix class that we have imported earlier, display, and then pass in here confusion underscore matrix equals CM, which is this CM array, and then display underscore labels. Let's pass display underscore labels equals train underscore dataset dot classes, or we can use our class names variable. So if you want to use our class names variable, it's here. We have the class names of the classes, or we might use also train dataset dot classes. I will use class underscore names variable because it's easier to write. And then let's go ahead. This is a disp function, or this is a disp now object. As you can notice in here, it's an object, sklearn library dot metrics dot plot confusion matrix dot confusion matrix display object stored at this location in the memory. The next step is to plot this display object. So disp dot plot, and then xtext underscore rotation equals 45. We need to rotate the xtext by 45 degrees, and then cmap, the color map, equals verdis. And then plt.title, we need to set the title as confusion matrix, or let's go ahead and make it a pretty confusion matrix. And then let's show it. plt.show, we now need to run the cell. 3, 2, 1. Wow, this is a beautiful confusion matrix. So we have a pretty confusion matrix. As you can see in here, we have the highest values lying on the diagonal here. So we have these values are really high. As you can see in here, the more the color that is going to or going towards the yellow, it's higher, as you can see here, and the colors that are going towards the DACA, it's small values. Okay, so but you can notice in here we have now this diagonal is the correct predictions, and they are really good. But if you see here, the model has been confused about the class cat with the class dog. So we have 73 samples or 73 images. The model misclassified. Okay, the model misclassified them between the class cat and dog, because that's reasonable, because a cat looks like a dog, and also we have deer. The model has confused a deer with a horse. So the model thought that 68 images were deer. In fact, they were horse. So we have this true label. This axis, y-axis, represents the true label, and x-axis represents the predicted labels. Okay, so the model predicted 68 images. The model predicted that they were deer. In fact, or in truth, they were horses. Okay, and so on and so on. Also here we have dog misclassified with 58 images with a cat. Okay, so the model predicted 58 images, predicted them as dog, where in fact they were cats, and so on. So this is the way that how to read a confusion matrix. So a confusion matrix is a really fun way to visualize your model's predictions and to visualize your model's performance. Now let's move on to the last step, or the final step in this lecture or in this video, and create a function that visualizes every time 9 predictions or 9 images and tell us what the model has predicted for this image and what is the truth label for this image. Now let's do it. So let's go def and then predict. Let's name it predict and plot grid. Let's give it a nice name. So predict and plot grid. It takes from me model. It takes from me dataset to predict on. It takes from me classes, so the number of classes, and then it takes grid size. The size of the grid equals 3. So you have 3 rows and 3 columns. So these are the parameters of the function. We have model, which model do you want to use to predict, and dataset, which dataset you want to predict on, and then we have classes, and we have grid size equals 3. Now let's set our model into evaluation mode. Always it's a good practice or best practice when you want to predict, when you want to make inferences, you need to set the mode of the model as eval. So turn the model into evaluation mode by using model.eval method. And then figure, axes equals plt.subplots. Let's create subplots. And then pass grid underscore size, grid underscore size. So we want to create 3 rows, 3 columns, and then fig size equals 9, 9. This is the size of the figure, 9, 9. Let's create a for loop for I in range of grid underscore size, and then create an inner for loop for j in range of grid size. So we want to create 2 overlapping for loops, for I in range grid size, and then for j in range grid size. idx, the index, equals random.randint, and then pass 0 to the length of dataset, -1. So we need to import the library random. We have to import random library. Okay. The next step is image. We need to get an image, true label equals dataset. This dataset, we need to index on the dataset and then pass here the idx index. And then input underscore tensor. We have to unsqueeze this image. So image.unsqueeze, and then pass in here the dimension as 0. We have to unsqueeze it. Why do we have to unsqueeze it? Because we want to add a batch dimension. Because if you want to visualize an image dot shape, this image contains 3 channels, and then the height 224 by the width 224. And then if you want to unsqueeze it, so unsqueeze and then specify the dimension as 0, and then if you get the shape, we will get a batch dimension now. So we have batch size 1 image, and then we have color channels red, green, blue, so the color channels, and then we have the height of the image, and then we have the width dimension of the image. So we have to unsqueeze it dot to device, and we need to move this image to the target device. Why? Because now our model lives on the target device, and in order to compute in this image, in order to predict on this image, the image also has to live on that device, on that target device. And then with torch dot inference mode, we need to turn on inference mode as before. Why? Context manager. Inference mode is a context manager that enables or disables inference mode in PyTorch library. And then we have to go output equals model, and then pass in here input tensor, input underscore tensor. So we have to pass the input tensor to the model, and then the model will produce a logits tensor, will produce a tensor of logits, and then we will store it in this output variable. Then underscore comma predicted equals torch.max. We need to use the max function and pass in here output.data comma 1. And then outside of this inference mode, we have to go outside of this inference mode scope. We need to define image equals image, and we have to unnormalize it by dividing the image by 2. So divide by 2 plus 0.5. And then we have to go numpy image equals image.cpu. We have to move our image back to the CPU.numpy method to convert it to a numpy array. Why? Because we want to visualize it. So we have matplotlib expects it as an numpy array, not as a PyTorch tensor. So yes, we have predicted using the model. The model is a PyTorch model, so it expects a torch tensor. But when we want to visualize it using matplotlib, it needs to be in the numpy version or a numpy array rather than in a PyTorch tensor. And then axes, this axis variable, which we have defined in here. So axes, and then specify I, j. I and j are just variables we are looping through. So for I and for j, we have to define the I, which is the rows, j as the columns. In this specific subplot, in this specific position of rows, for example 1 or 2, and columns, whether it was 1 or 2 or 3, we have to imshow. Imshow is short for image show. We have to implement the function imshow and pass in here numpy.transpose. Since matplotlib also expects the shapes to be as height, width, channels, and PyTorch likes to deal with images in the shape of channels, height, width, we need to transpose this image tensor and go numpy image, comma, and pass here 1 to 0 as we said before. And then color equals classes. So classes, and then true classes, true class or true label. We want to index on the classes by using the true label. So classes, we will pass classes over here, and then we will index on classes by using the true label, whether it was horse or frog or ship or automobile. We will index on the classes, whether it was, and if it matches classes and then predicted dot item. So if the prediction, this line says here, if the prediction matches the truth class, or if the prediction matches the correct class, then we will, if color, if it matches up, if true, we will set the color to be as green, else we will set it to be as red. So color equals red, R. And then axes, and go I, comma j dot set title. We have to set the title of the subplot to be as f string truth So the truth, which is classes and then index on the true underscore label, and then put a backslash in here, and predicted, comma, the predicted label as classes pass predicted dot item. And then we have to set the font size to be equal for 15 as 15, and then C or color equals color. Or we can make the font size as 10. And then plt dot tight layout. So this function tight layout, and then plt dot show. Now I believe that this function will work now. Let's go ahead and call this function. So let's go ahead and call this function predict and plot grid. Predict and plot grid function, and then we have to pass in a model. Our model, we have to pass in test dataset, comma, we have to pass in here train underscore dataset dot classes. Now I think it will work. Test dataset, yeah. Now let's go ahead. 3, 2, 1, run the function. Whoops, we have got something wrong. I think here predicted dot item. So I think if you go here, show numpy transpose, we have to turn axis off. You have to go axes, and then I, j dot axis off. We have to put these outside of the for loop. Yeah. So the error here, the indentation was should be off by 1 step. The indentation of this should be off by 1 step. Okay. So indentation is a big problem in Python. Now let's run this. Run this again. Hooray! Now we have these images. The same idea here. plt.tight off, tight underscore layout, plt.show, yeah, these 2 lines should be off by 2 indentation steps. Okay, now let's run again. Yeah, yep. So indentation in Python. Now we can notice that the truth is bird. This image represents a bird, predicted that it's a bird, and that's good. So now notice our vision transformer model is predicting on these images, and these images are images that the model hasn't seen during training. It's new images. They are images outside of the training dataset. They are images that the model has never seen before, and the model is predicting correctly on it. So this image, truth is bird, predicted it's a bird. Here, truth is airplane, predicted it's an airplane. Truth is a bird here, and predicted it's a bird. So that's a really good thing. Here also we have truth cat, predicted it's a cat, even though the image is pixelated. Truth is airplane, predicted that it's an airplane. And every time we run this function again, we will get different set of images. Now we can notice here, you can notice in here, truth is a bird, predicted that it is a bird. And for example here, truth is a truck, predicted that it's a truck. And the same idea goes on. Every time we run this function, we will get different images. So if you run again, we will have here, truth truck, predicted it's a truck. So all the predictions are correct until now. Now let's do one more for good luck. Maybe we will get wrong predictions here. Yeah, now we have this image with a wrong prediction. So truth is a horse, but the model predicted that it's a deer. So this is an example of a prediction of a wrong prediction. Now let's run again. As you can see in here, truth bird, the model predicted that it is a bird. Okay, so the model matches the truth. And you can so on until you get here truth is a dog, predicted that it's a bird. Oh. And you can notice in here, this is an image of a frog, truth is frog, predicted that is a frog. Nice, correct. Here we have truth automobile, but the model predicted that is it. It's an airplane. So you can visualize many more predictions as you want, and this is the project of, as you can see here, in here, truth is a horse, and the model predicted that is a horse. So this was the Vision Transformers project, a PyTorch based exploration with CIFAR-10 project. I hope this project has given you something new to learn, new ideas or new codes, and for that I hope to see you in new lectures. Thank you for watching. That's it, and see you later. See you in a new lectures.